The next group of fields I want to talk about are all in support of the concept of fragmentation. And fragmentation, we'll talk about it more as we go through this, and I'll show some examples and we'll actually look at some packets. But what you need to know is fragmentation is a feature provided by the network layer and by the Internet Protocol that allows a system to take a large packet and break it up into groups so it can be reassembled later by the recipient host. And there's a number of reasons that might occur, but that's generally going to be related to networks that have lower maximum transmission unit sizes. Now, in support of this, we have a few different fields. The first is at the 4th byte offset from 0. It's a 2-byte field, and it's the identification field. And this field is used to uniquely identify packets or groups of associated fragmented packets. It's not exclusively for the purpose of fragmentation, although it does help associate those together. But you should see that each IP header will have an identification field, and that will be a unique value for every independent packet, whereas fragmented packets will have the same identification value. So you see that there. It's the first field on the second row, the identification field, and it's a 2-byte field. Next, we have the flags field, which is at IP6, and you see that right after the identification field there. And it's only a 3-bit field, so we don't see a lot of those. We don't see a lot of we see a lot of 1-bit fields and 4-bit fields and 8-bit or 1-byte fields. We don't see a lot of 3-bit fields, but that's exactly what the flags field is, and it contains 3 individual flags. One of those is the reserved flag, which was reserved for a future use, which some custom protocols will use it for some various different things, but for the most part, it's unused. We have the don't fragment flag, which when set will instruct devices receiving packets not to fragment them under any circumstance, and we'll show an example of that later. And then we have the more fragments flag, which is used to indicate to a receiving host that this packet is followed by more fragments that are part of the same larger packet that should be reassembled. So we have those each individual 1-bit flags, either a 1 or a 0, they're set or they're not. After that, also an IP6, but going for 1 byte and 5 bits in addition to that, is the fragment offset value. And this is used to facilitate the fragmentation and reassembly of packets so that they can be reassembled in the appropriate way. So rather than tell you about that, I want to talk a little bit more about fragmentation at a high level and go into some examples, because it's a lot easier to understand how these 3 fields work in concert when we actually show you examples of that. So let's go ahead and do that now. Fragmentation is provided as a feature on the network layer because traditionally different networks have had different allowable sizes of packets that could traverse the networks. This is generally managed by something we call an MTU setting, which stands for maximum transmission unit, and that's the maximum packet size that is acceptable on a network interface. Now, for most networks these days, that's 1,500 bytes, not including the 14-byte Ethernet header. So 1,500 bytes is what that generally is, but that wasn't always the case, especially back in the early days of networking. It would be much lower in some networks, and some people would intentionally set it lower to decrease network congestion or for a variety of other reasons. All that said, it's not as big of an issue today. It's not something we see as much on modern networks, but the service does still exist, and it exists at the network layer and allows the protocols like IPv4 to take a single packet, look at that MTU value that it knows for the network it's trying to send to, and break the packet up into allowable chunks. So if the MTU of the network is 500 bytes, the 1,500 byte packet could be broken up into a few different packets. So we'll go through an example of this and I'll show you exactly how it works. But again, the thing to know is that fragmentation isn't seen as much. I'm not going to say you'll never see it. You probably will see it a lot, especially with some types of VPNs and network tunnels and things of that nature. That said, because it's not seen often though, a lot of network owners don't actually allow fragments into their networks at all. If they see a fragmented packet, they drop it right at the router and they won't allow that. And the reason is because fragmentation has been used maliciously in a number of ways in the past. One way is that it's been used to evade intrusion detection systems by splitting up specific types of content across multiple fragments, tripping up how intrusion detection systems might review that data. There's also been a number of fragmentation attacks. You may have heard of teardrop attacks or the ping of death. Those are different attacks using fragmentation that exploited vulnerabilities in the code that's used to reassemble packets. And I'll show you an example of a couple of those here in a little bit. So fragmentation is a little less important now than it used to be, but you will still see it, and certain protocols still use it. So it's important to understand exactly how it works, which is why we're going to spend just a little bit of time talking about it here and going through a few examples and different types of stimulus and response. Now, as I mentioned, fragmentation relies really on three fields. We talked about at least two fields. We talked about IP identification and fragment offset. We talked about a couple different flags, but the one we're really interested in here is the more fragments flag. We talked about the don't fragment flag, and we'll talk about that in a bit. But for packets that you actually want to fragment, it's going to be a concert of these three fields: IP identification, fragment offset, and the more fragments flag, that are going to allow that to happen. So let's actually take a look at an example of what packets might look like when they're fragmented. Let's go through an example of normal stimulus and response where we need to fragment packets in order to get them to their destination. Now, under normal circumstances, we would have system A and it wants to send to system B. And system B is on a network where it can receive traffic at the standard 1500 bytes per packet. That's its MTU setting, which is what you'll see on most modern Ethernet networks. In this case, if I want to send a single 1500 byte packet to system B, really straightforward. I just send it using the normal stimulus and response pattern we've already discussed for IP-based communication. However, what if I want to send to system B and system B is on a network whose MTU is only 600 bytes? Well, that's a bit problematic because 1500 is a lot more than 600. I know I promised there wouldn't be a lot of math in this thing, but I think you can handle that one. So if I want to send 1500 bytes to system B, I'm going to have to break it up a little bit. I'm going to do that via fragmentation. So what I'll do is instead break this packet up into three separate fragments, and I want to walk through those with you now. The first packet I'm going to send is going to be 600 bytes. It's going to have an IP ID value of 5F, 4F, which is going to be used to identify this entire fragment train. The more fragments bit, which is identified by MF there, is going to be set to 1. And that indicates to the receiving system, hey, once you receive this packet, there are more packets coming to complete this fragment train. So you'll have to reassemble those, is basically what it's telling to system B. Finally, fragment offset is set to 0 because this is the first fragment in this train. That will go up as we go along. So in this case, you see down there at the bottom, this is the received fragment train from system B. So we have fragment 1 sitting down there, size 600, fragment offset 0. Next, system A sends the second fragment. This is also 600 bytes, and you'll immediately notice it has the same IP ID value of 5F, 4F. Again, all these fragments will have that same value, and that's how system B ties them all together. The more fragments bit is set to 1 again, which means there's another fragment coming, which is what we would expect. And the fragment offset is set to 600. That's basically taken from the first packet. We first sent 600 bytes, so the second fragment is 600 bytes. And this exists so that when system B receives the second fragment, it knows where it goes in order. There's a very good possibility that these fragments could be received out of order, and by looking at that fragment offset value, system B knows how to piece those together. And of course, it gets fragment 2 and puts it alongside fragment 1 and continues to reassemble this fragment train. Finally, we have the third packet that comes through, and this one is going to be 340 bytes. We see it has the IP ID value of 5F, 4F, so we know it's associated with this fragment train. The more fragments bit is set to 0, which means there are no more fragments, so it's the end of the train. It's the caboose, if you will. And the fragment offset is set to 1200, accounting for the 2 fragments we've already received. Each of those was 600 bytes. We add that together, it's 1200, so the fragment offset is 1200. Once that's received, we see that down there below. The fragment train is completed, it's assembled, and it can be processed by system B as a single individual packet. So we're all done there. Great. However, did you notice anything odd about the size of these packets that we just talked about? Did anything stand out to you? Well, the packet we wanted to send was 1500 bytes. However, if we add 600 bytes plus 600 bytes plus 340 bytes, those 3 fragments, we actually get 1540 bytes. Where did those extra 40 bytes come from? Can you think of why those would be necessary? Well, consider this. Each fragment is now being sent as a completely new packet. What do we need in order to send a packet across the network to another system? Well, we need another IP header, right? Because in the first packet, we only needed the one IP header to get all 1,500 bytes across. Since we're breaking this up into 3 different packets, each one of those requires an IP header. So we already had one IP header. We're adding 2 of those for the additional 2 fragments. The IP header is 20 bytes by default. So we add an additional 40 bytes to the size of things. So it decreases the efficiency of the communication a little bit in that regard because we are adding those additional 40 bytes, but not a big deal overall. However, it's something you do need to account for when you're reviewing and processing packets, trying to understand those when you're looking at those in Wireshark or in another tool, is that based upon the number of fragments you have to break the communication up into, you will have an additional IP header for each one of those. So typically, you'll be adding an additional 20 bytes to each one of those. And that's why we have 1,540 bytes in our fragmented example versus just 1,500 in our non-fragmented example. But again, this is normal stimulus and response for IPv4 fragments, if you consider fragmentation normal at all. Some people do, some people don't. It's really up to you. As I said, some people don't allow fragments into their network at all, and they consider any fragmentation abnormal. I'm not saying I'm willing to go that far quite yet, but I will say that no matter what, fragmentation itself, when done in this manner, is normal as a part of a service that the IPv4 protocol offers. Next up, let's look at some actual packets that show some fragmentation going on at the IP layer. I don't just want to talk about this, I want to show them. This won't be as pretty and as clean of an example as I showed on the slides because I can't have everything on the screen at once, but I do want to show what these look like so you're familiar with dissecting fragmented packets in Wireshark. This packet capture is included in the captures you can download with the course, IP_frag_source.pcapng, so you can play around with this yourself. And in this case, we have 6 packets here, and this is an ICMP ping being sent out from one host to another. So it's being sent from 10.10.0.3 to 192.168.0.128. We haven't talked about pings or ICMP yet, but that isn't really relevant. All you really need to know is that ICMP relies upon the IP protocol, so we have IP headers in here, and that's where fragmentation can exist. So let's actually step through a couple of these packets. Again, these first 3 are all part of the same request. So we have one actual packet that's been fragmented into 3 packets and sent along. If we look at the packet the packet list pane, one of the first things you'll notice here is that the first 2 packets identify in the info column as just fragmented IP protocol. That's all they say, but they do have a lot of the useful information we want to see here. So we see the offset of this first one is 0. We see the ID of it is 7474. We would expect the offset to increase, and here it does, from 0 to 1480, 1480 to the next value. We see the ID stays the same, so the ID of this fragment is 7474. The ID of the next one is 7474. I believe that's actually in just decimal instead of hexadecimal. So we have that data there, and we actually even see some metadata that tells us it's reassembled in number 3. And I say this to show you that no matter how many fragments there are, you will actually just see this fragmented IP protocol info value until you get to the final packet in the train, or the caboose again, if you will. So in this case, it says reassembled in 3, and if we go to packet number 3 here, we see what the packet actually is, and it's being dissected now properly as ICMP. Know that all of these packets contain ICMP data, but they're only reassembled and shown as ICMP in this third and final packet. And that's done that way pretty consistently. So that's just how Wireshark chooses to interpret and show that information, which is fine as long as you know what that looks like and how that relates. If I look down here into the third packet, into the packet details window, you see that Wireshark actually provides some of the reassembly information. So if you find a packet that happens to be fragmented, but you come in on the end of the train, you can actually expand down here and it'll show you the different packets. And this are frame 1, 2, and 3. So I could click these and it'll actually take me to them. If I look at the totals here, you'll see that each one is 1,480 bytes, and the final one is 548 bytes. And we have a total of 3 fragments. Our final reassembled length here is 3,508. And of course, we have all this reassembled IPv4 data, which it's talked about here, which is actually our ping packet. Of course, if I close this header down, you'll see that we have our ICMP header here as well. But if I scroll up to these other packets, you won't have that ICMP header. You'll again only see the full reassembled IP header in the final packet in the fragment train. So that's important to keep in mind. But otherwise, we see a lot of the things we expect to see. We see our offset is incrementing by the number of bytes transmitted in the previous packet. We see that our ID values are remaining the same, both in the request and in the response here. And everything shows normal stimulus and response regards IP fragmentation. Now, one thing I will do if I happen to be troubleshooting an issue related to fragmentation, or maybe I'm looking at some type of fragmentation-related attack, is I'll often take the IP identification field here, and I'll right-click that and apply that as a column. And I do that because the way the ID is shown here on the right in the info column, it's not really lined up really well, and it's really hard to scroll down and read all those. So if I break that out into its own column, it makes it a little bit easier to read, and we actually get the hex and the decimal representation here. I think I actually said earlier that this 7474 was decimal. That's actually the hex representation, and then over here in parentheses is the decimal representation. Doesn't matter which one you use as long as you're making sure they're consistent within each fragment train. So that said, that's fragmentation. You've got this packet capture. You can play with it. If you really want to learn more about fragmentation, the best way I think to do it is actually generate some fragmented packets. So you can actually specify the size of the pings you send to other hosts. So one method to do this is to specify a particular large ping, ICMP ping from your Windows or Linux host. Send that to something where you know the MTU on the other end is smaller, so maybe just send a 3,000 byte ping and capture the fragments there. You can also use tools that are actually designed for attacks. One of the most common is called Frag Router, and it will actually take all of your traffic and break it into fragments. It's really designed for IDS type evasion attacks, but you can use it just to learn a little bit more about IP fragmentation. So again, in this course, we cover IP fragmentation because I want you to know how it works. It is a normal feature of the Internet Protocol and how it works. That said, I don't see a lot of fragmentation out in the real world, so consider that when you consider how much time you want to invest in devoting to learning more about fragments. But nonetheless, it's an important piece of knowledge when you want to understand IPv4. So how do we know if we need to fragment packets if we're trying to communicate with a system we've never communicated with before? After all, every host on the internet doesn't maintain a list of the MTU setting for every other host on the internet as well, right? We have to be able to figure that out dynamically. And I'm not going to go over that process in too much depth because I don't think it's entirely relevant or entirely practical for everyday use. But I do want to go over a couple of normal stimulus and response scenarios related to the transmission of oversized packets, because it can look abnormal if you see this the first time. But if you know that this is normal traffic, then you can just move on and kind of dismiss it. In this case, let's say we have system A that wants to send to some other endpoint somewhere and has to go through a router, and that router knows that the next hop MTU, or the next whatever the next hop along the packet's path is, knows that the MTU is 1,300 bytes. But in our case, we want to send a 1,500 byte packet through that router. Well, the cool thing about the router is it's actually going to do some of the work for us, and it's going to fragment those packets most of the time on its own. So it's going to break those up into the appropriate packet sizes and send IP fragments out. System A actually doesn't have to do the fragmentation because the intermediate router is going to do that. And that's something you'll commonly see is packets will be fragmented out on the internet and be reassembled and come back to you, and you'll never know they were ever fragmented because it's obviously a pretty seamless process. However, what about, and this is an important scenario to consider, is we have the don't fragment flag. What happens if I want to send 1,500 bytes to this router and it knows the next hopped MTU is 1,300 bytes, but the don't fragment flag is set? Well, that's an interesting use case, and it's actually going to bring in another protocol that we've not yet examined, and that's the ICMP protocol. ICMP is a bit of a utility protocol. It's used to provide information and help systems administrators do a lot of different things, and this is one of those. In this case, if System A sends this 1,500 byte packet that's too big for the next hop with the don't fragment flag set, the router is going to send back an ICMP Type 3 Code 4 packet, which means the destination is unreachable because the packet is too big. At that point, System A can fragment the packet up itself or do some other type of wizardry with the application layer protocol to break up the data size into a smaller chunk and then retransmit it to the destination host so that it can make it across the networks it's trying to traverse to get wherever it's going. So that's really the purpose of or at least the interaction we see when the don't fragment flag is set. You might ask yourself, well, why would someone set the don't fragment flag? And again, that's kind of a little bit of an artifact of older networks. Some folks would set the don't fragment flag if they were concerned that fragmenting the packet would cause some type of issue with the performance of their service, or mess something up. It would break something along the path. So that's a flexibility option that exists in the IP header, and there's a number of reasons for it. But you don't really necessarily need to understand all of those reasons, so to speak. But I do want you to understand that this normal stimulus and response exists. Wherein if we send something with the don't fragment flag and we encounter a lower MTU, we're going to get these ICMP codes back. So if you see those, you know what you're seeing. Next up, I want to talk about abnormal stimulus and response related to fragmentation. And I mentioned earlier that there were a few reasons administrators may actually not allow fragments into their network at all. One of those that I mentioned was the potential for IDS evasion. Of course, intrusion detection systems, or IDS, they sit generally at the network border, sometimes other places, and they monitor network traffic into and out of the network or into and out of a specific network segment. And that's kind of what we have represented here. We have a source and a destination communicating with each other, and we have our intrusion detection system that's really monitoring everything in place. Now, intrusion detection, at least signature-based intrusion detection, works by examining the contents of packets and looking for things that are of interest. So we build these signatures that look for known bad things, and then we look at individual packets and we try to find those bad things. In this case, we have our source sending a packet to our destination with the string evil string in it. So we could build an intrusion detection system rule that looks for evil string, and if it sees this packet, it's going to flag on that, and we're going to detect it, and everything's great. However, I want you to consider this scenario. Instead of sending a single packet with evil string in it, what if we fragmented it? What if we fragmented it like this, where EVI was in fragment 1, LST is in fragment 2, and ING is in fragment 3. So we still have the same string, but it's broken up across 3 different fragments, and it's still going to get to its destination and reassembled. So we're still going to be doing the evil thing we're doing, but it's going to be broken up such that the IDS may not be able to see that. Well, that's an IDS evasion technique, and for a long time, it was a very productive and successful evasion technique. However, the good thing is most intrusion detection systems now, especially things like Snort and Suricata, they actually automatically do packet reassembly. So they're able to cache these fragments as they receive them, reassemble them, and then examine the entire stream. And it does that both with IP packets or with TCP streams, all kinds of different streams. Most of these IDSs will reassemble and examine the whole stream instead of the individual packet. So we've evolved past that point. However, one of the tricks with fragments is that every operating system processes fragments a little bit differently. They use a little bit different rules. So different versions of Windows will do it a little different way. Windows will do it a little bit different from Linux, and so on and so forth. So in order for you to reassemble IP fragments properly, you actually have to maintain a mapping within your intrusion detection system of every host on your network and all the operating systems so that the fragmentation policy can be set accordingly. Otherwise, it's going to use some default or base configuration for fragmentation reassembly, and it may not always get it right. That is to say that the intrusion detection system may not always see the assembled packets in the same way that the target operating system or destination operating system will. So that gets a little tricky. And furthermore, quite honestly, I don't see a lot of intrusion detection systems deployed where people go to the effort of importing this list of IP addresses and different fragmentation policies for different operating systems so that the fragmentation policy can be defined. So not a perfect thing. Fragments can still trip up IDSs on occasion, not as much of a problem as it used to be, especially as people are settling on more consistent fragmentation reassembly policies, more consistent. But this is one of the reasons why many administrators choose to drop all inbound fragments at their border, not deal with it at all. They'll maintain a normal 1500 byte Ethernet MTU, and they expect people to comply to that, which is not a bad policy. But this is ultimately how IDS evasion can work with fragmentation. Of course, there are a lot of different variations on this, a lot of ways to evade IDS. This is just one of them, but this is really the simplest way to explain it, or at least the simplest use case. One more category of abnormal stimulus and response I want to discuss are vulnerabilities related to fragmentation. And these specifically relate to vulnerabilities in the systems that process fragments. Really, anytime you build a system that takes in data and has to process it and reassemble it, you have to recognize that you're going to be opening yourself up for the potential for weird input to come in that is unexpected, and you have to be able to handle that, or else you encounter vulnerabilities that can lead to a denial of service condition, or even worse, some type of remote control. And these are more related to denial of service, but traditionally, a lot of operating systems, both on end user systems like workstations, as well as on things like routers, had trouble handling certain types of inputs that came across the wire when it came to fragmented packets and then reassembling those. I'm talking 10, 20 years ago. I'm talking about systems that back when security obviously wasn't as big of a deal as it is now. Now, that's not to say some systems still don't fall victim to these things. They do, but they're not nearly as common, so I'm not going to spend a lot of time on them. But I do want to talk about two of the most common types of attacks. The first is called the ping of death attack. And in this case, we have a source sending to a destination. It's going to send a whole lot of fragmented packets. Now, these packets are probably going to be whatever the maximum MTU size is. And it's going to send enough of them such that when that series of fragments is received by the destination and the destination goes to reassemble them all, the size of the packet will be greater than 65,535 bytes. And what this does on systems that were vulnerable to this attack was allowed an overflow of the buffer space for that connection, that fragmentation reassembly cache. And in this case, it would actually crash the system. And that's why it was called a ping of death, was by sending a ping. In this case, we're talking about an ICMP echo request, which uses the IP packet. So by sending a ping, and using the IP protocol in that way and fragmentation in that way, you could actually crash the system and it would just go down altogether. Now, that's pretty bad, and you got to figure someone's going to get on that and fix that pretty quickly. And for the most part, it persisted for a while, but it was fixed. I don't see a lot of systems really vulnerable to this anymore. I won't say never, because as recently as a couple of years ago, I was doing a penetration test for an organization in a utility, and they had some individual devices that were deployed out to a bunch of their locations that were responsible for managing this utility. And I got access to these and started playing around with them and found out they were really high latency, very slow, and they seemed to act in ways that I would think would be very familiar of old embedded devices. Sure enough, I sent a group of fragmented packets and sent a ping of death to these machines. And sure enough, they all went down. I crashed every single one of them in this test environment that I was in. This was in a production environment. In this test environment, and come to find out, they were using a very old version of a TCP/IP stack, which was reassembling these things in a vulnerable way. And as a result, the ping of death I found was still alive and well. Very unfortunate, but goes to show you some of these things that are old become new again, and that's one of the reasons I take time to mention at least a couple of these attacks. The second attack I want to talk about, in this one we have a source and destination, and we're going to send fragments to it. Now in this case, I want you to notice something different. In fragment 1, we send 1,000 bytes. In fragment 2, we have a fragment offset of 800. Well, wait a minute, isn't the fragment offset supposed to be equal to the value of the bytes that have been sent to that point? And you're right, it is. Fragment 2 is another 1,000 bytes, and we still see in fragment 3 that we only have 1,100 bytes when we should have 2,000 bytes. What we have here are overlapping fragments. So if you actually were to try to reassemble these, it's going to be a little confusing because packet data is going to overlap if you try to cram 1,000 bytes after 800 bytes when you have actually 1,000 bytes of data. So that's going to confuse the interpreter. And we have a lot of systems a while back that were really confused by this, and they would end up crashing as well. And this was actually called a teardrop attack. This isn't one I've seen recently, not as recently as I've seen the ping of death. There are still systems that are vulnerable to this, but not very many, not any modern systems that you're going to see. Most everything's patched against this. But it is probably the second most popular of these fragmentation attacks after the ping of death. So certainly worth mentioning in the context of abnormal stimulus and response. So there are a few different variations on these types of attacks. These are probably the two most prevalent and most common that I've seen discussed. And I don't think you'll necessarily see these around, but I do bring them up just to show you ways that fragmentation can be abused and really ways that protocols can be abused. Remember, no matter what, when you send data with a specific protocol, you have a system sending, a system receiving, and who knows how many intermediate systems, and they all have to be able to send and process data in the same way. And it's those variances, those differences in how that data is processed that can lead to potential security issues. So that's something to keep in mind as we go forward and look at any of these protocols when we talk about abnormal stimulus and response related to them.